Hello everyone, my name is Tianzheng. In this video, I'm going to make some comparisons in terms of price and performance for persistent memory and modern next generation SSDs. This is joint work with my students Kaisong and Darien from SFU and in collaboration with Dongjie from Penn State. Let me start with the traditional storage hierarchy. We can have different layers, but in between different layers, there is a clear boundary. For example, memory is fast but volatile. Storage devices such as SSDs and HDDs, they're slower than memory, but they're persistent. Based on this hierarchy, most database systems are actually caching stores. They cache hot or frequently used data in DRAM using a buffer pool and persist modifications to SSDs as needed. This is very cost effective and has been hugely successful in the past few decades. However, this hierarchy is actually being disrupted by two trends. The first one is persistent memory, or PM, which in general is a type of device that offers bioreversibility, persistence, larger than DRAM capacity, and also cheaper than DRAM price on the memory bus. Because it's on the memory bus, we can use load and store instructions to access data without having to use a file system. Currently, the only product we can buy for PM is Intel Optane DC PMM. Here I'm showing the performance characteristics of the latest 200 series model based on the 3D cross-point technology. For read performance, we can get up to 7.4 gigabyte per second bandwidth, and for write performance, we can get up to 2.3 gigabyte per second bandwidth. And the capacity-wise, a single DIMM can have up to 512 gigabytes of capacity. So this is just the numbers for a single DIMM. If we have multiple DIMM plugged in onto the motherboard, then we can have a much higher aggregate bandwidth and the capacity. So with this kind of numbers, then if we fit this new device into the storage hierarchy, then we will realize that we still can have the traditional DRAM, volatile DRAM and memory layer, but now we can actually have a newer layer, which is the persistent memory layer. Nevertheless, it is still memory, although it's persistent. So we can find that when we talk about the memory in this new hierarchy, memory isn't necessarily volatile anymore, but rather we can have persistence in the memory layer as well. This has led to a lot of exciting development recently in our community for building essentially single-level stores instead of using buffer pool and SSD. The main idea is that we build index structures, for example, B trees and hash tables that directly persist data and operate on top of persistent memory instead of going through a buffer pool to exchange data between DRAM and the storage devices. This has received a lot of attention, and there's perhaps hundreds of papers already describing these ideas. So here, SSDs are actually catching up very quickly with high performance, and they're built usually using newer material, for example, 3D VNAND or 3D cross-point, which is exactly the same material that's used to build persistent memory in the previous slide. They're also usually in newer interconnect, for example, NVMe Gen 4, and also can leverage newer software stack, for example, SPDK and IOUring. In the news, probably you have already heard that we can even get more than 10 million IOPS on a single core on these newer devices. So these are amazing numbers, and there are many different devices like that. But one particular device is very interesting, which is the Optane DC SSD, which uses the same material, like I said, for building persistent memory in the previous slide. So here, as we can see, for this particular drive, we can actually get both read and write performance at 7.4 gigabyte per second. And the capacity-wise, we can get up to 1600 gigabyte per drive. If we have multiple drives, then we can further increase the aggregated bandwidth and the capacity. Now, because it's using the same material as PM, it becomes a very interesting comparison to make with the DC PMM devices. So here, if you still remember the numbers I reported in the previous slide, you will realize that actually for DC PMM, which is the memory form factor device, we're actually getting lower performance for write operations at 2.3 gigabyte here, compared to the 7.4 gigabyte per second in the SSD version. Notice here they're using the same material. So overall, we can see the trend is that SSDs are actually approaching memory speed, or in this case, it's even actually faster if we have only one DC PMM on the motherboard. So this leads to a very interesting phenomenon, which is called the storage jungle. So now we don't call it a storage hierarchy anymore because the layers here now, they have overlapping properties. It's not a clear boundary anymore. And in particular, memory is not necessarily volatile, and storage devices, they're not necessarily stored in memory anymore. So as software developers, we think about how we can use these devices to actually build data structures and other components in database systems. We have already talked about what the PM camp is doing. Now, with this new SSD devices, the SSD camp, which is relatively quieter because this has been perhaps the way we do things from day one. The question to ask here is that with fast SSDs, can we actually make indexing structures to match or even outperform PM index data structures? And furthermore, we would like to also explore how much we're actually paying for the performance we get from either approach. Let's first look at the cost, and then we will add performance back into the picture a little bit later. When we consider the cost of a storage server, we need to consider three things. First of all, it's the storage device itself, of course, which can be DCPMM and SSD in our case. And also we need to consider the CPU and DRAM cost, which are the actual devices that allow us to access data stored in the storage device. Let's start with persistent memory on the left. It has very rigid installation requirements. We have to follow strict population rules about DRAM DIMMs and DCPMM DIMMs. For example, for each controller, we have to have at least one DRAM DIMM to be able to even boot up the machine. We also have to often clock down the memory subsystem frequency because persistent memory DIMMs, they typically run at a lower frequency compared to DRAM chips. But SSD devices don't really have such requirements, and nothing really is over-provisioned. Now, coming back to PM, it also has a very non-trivial CPU cost because to access data, we're actually using synchronous load and store instructions. And notice that the CPU here has to be certain models, and they tend to be very high-end to support persistent memory. So we might be actually wasting high-end CPU cores on just moving data instead of running application logic. But again, SSD devices don't really have this problem because we can overlap I/O and compute using asynchronous DMA programming model. When it comes to the actual dollar amount, if we only consider the storage media cost for PM, each DIMM here for 128 gigabyte model, we're paying about $4.27 per gigabyte. But when you add the DRAM and the CPU cost, this number suddenly becomes $18, over $18. Meanwhile, if we consider the SSD side, the per gigabyte for the SSD device itself is just $2.66 per gigabyte. And even after we add DRAM and CPU cost, it is still below $6, which is 1/3 of the cost for the PM server. So here, as we can see from the numbers, actually the DRAM and CPU cost, they subvert PM's cost effectiveness. Now let's look at performance per dollar numbers. So we tested three tree structures. Two of them are PM tailored, FP tree and BZ tree. And for B plus tree here, we coded up very quickly a coursework grade code base that uses a buffer pool on top of this P4800 SSD. Notice that the code is still correct, but it's not really optimized in any way. On the right-hand side, I'm showing the result. There are many lines over here, but I want to draw a couple of highlights here. The first one is that if your workload is actually memory resident, then definitely use an SSD plus DRAM because it's well worth it to actually add more DRAM to get better performance. In other words, the extra cost is totally worth it for the increase in performance. The other thing I want to highlight is that if we consider the performance delivered by a single SSD drive here, which is denoted by P4800X1, it's actually quite competitive with the corresponding 1 DIMM version of PM here, which is denoted by the PM1 variant. So the performance numbers and also the cost of performance numbers, they're very competitive with each other. We have more details in our paper, and in the future, we hope to also interleave both SSDs and PM to get a full picture. So finally, let me summarize with a few implications and then give some outlook. First, PM hardware still is too expensive. Especially we have to add high-end CPU cores for I/O, or quote-unquote I/O here, meaning data movement. And also we have to over-provision a lot of DRAM in this case. It's also expensive to actually deal with the software stack for PM because we have to learn to program it. It's really different compared to programming, say, SSDs or DRAM-based volatile data structures. We also might have to co-design hardware configuration with software. For example, we might face this question: how many DIMMs do you actually need for this particular tree structure? Because different tree structures, they have different designs, so they might need different numbers of DCPMM DIMMs. Now, we also have two small wishes, which are pretty important for persistent memory to make sense in economic sense. So first of all, we want the per gigabyte price to drop. And also, more importantly, we want actually the population restrictions to be lifted so that we can actually focus more on the storage device itself rather than the other enabling components such as CPU and DRAM. On the SSD side, here, I hope I convinced you that from our numbers that they're actually great, and the modern SSDs, they're fast, and you should actually use them, at least before considering using PM for future data structures. They're usually more cost-effective, even with suboptimal implementations, as we have seen in the previous slide. There's many exciting directions with new data structure designs, for example, using SPDK, ZNS, and other directives that's coming up in newer SSDs. Now, of course, if the application actually needs PM level low latency, then we have to use PM. But so far, it looks like such applications, they're quite few. That's all I want to talk about. Thank you for your attention.